Okay, thank you. Good afternoon. So I'm actually one of the organizers, so that's why I'm asked to give one of the lectures here. So I'm not actually going to teach. So basically my role will be two types. Here there is another role that I'll be discussing, but my personal role will be two types. One is as organizers, I'll try to, like there are some gaps that I'll try to, remove that gaps, like some talks we had before. And second thing is, if you see that, most of the spectroscopy talks were on experiments. So I'll try to, motivate you that even theoretical studies on spectroscopy also, they are very important. And as we go on, we'll see that how they are important. When we talk about precision studies in spectroscopy, so most of time, like I'll be talking about these properties. And I'm sure that, those who are working on atomic spectroscopy or even other also you'll be, using some of these, quantities in your experiments for doing analysis or even for theoretical studies and so on. So I'm talking about the atomic clocks that was already discussed, and then how the theory is going to help you in that. And then I'll also mention about this high precision measurements of isotope shifts, and these kind of quantities like BBR shifts, Stark shifts, Zeeman shifts, how they'll be useful if you can estimate them precisely. And also today morning, like we had one talk on the CP evaluation or parity evaluation, studying BSM physics, using atoms and molecules, and how the theory plays the important role there. That also we'll try to understand. There are also other quantities that like the methods I will be discussing. Using that, you can study all these properties. Okay, so there are some discussions today morning about studying BSM physics, but then there are also some comments that like what's the point of studying this kind of physics, even there are other groups who are doing that. So as you know that the standard model of particle physics that deals with three fundamental forces, and it has 12 fundamental fermions, 12 gauge versions. And it gives us parity evaluation. That is one of the discoveries of this, which describes the standard model, like what we, even that is observed. And using standard model, we can also explain CP evaluation, T evaluation effects that is also there observed. One of the most outcome of this model is it unifies two fundamental interactions, electromagnetic and weak interactions. Okay, and CPD is also conserved under standard model of particle physics. But as it was mentioned by Amar, that we see more matter than antimatter, and one of the reasons for that is we need to have because of CP evaluation, the kind of CP evaluation that standard model predicts, that is not going to explain the reason behind this matter antimatter asymmetry in the universe. So we are looking for some kind of more sources of CP evaluation that will help us to understand why we see more matter than antimatter. Then there are also questions that why we only have 3 generations of quarks, why not more? Okay, and there are like dark matter, dark energy exist, that was discussed. So now if you want to describe this kind of physics, so standard model cannot do that. So that means obviously the standard model is not a complete theory. It's an intermediate manifestation of some complete theory that these people are trying to prove. That is the main motivation. Whether that is your interest or not, that's a different issue. Now, because of that, they have proposed several models. Okay, because that is also known or not known that which theories are complete. So they, based on some scientific arguments, they come up with different models, thinking that that could be the ultimate theory. One of the famous model is supersymmetry model. So what it predicts that the number of particles you have in the standard model, you will have the same number of particles, another like a mirror reflection of that. But wherever like here you have fermions, the corresponding particles will be the boson and so on. Okay, so now if you consider this kind of models, then this will introduce more number of intermediate particles, more type of interactions among the particles and so on. Then the kind of like interactions we are talking about generally we consider in our systems, then that possibility will be it will increase. Then you may see some kind of new phenomena, and that we are trying to discover using atomic and molecular studies. Okay, and why atomic and molecular? It was already Amar had already explained that, but I will give you a different kind of intuition to that to explain to you that a little better. So now to study this kind of fundamental particles or their physics, you need this kind of accelerator methods like in CERN and so on. But why we need this kind of facilities, such a huge facility? Because of this fundamental like principle, that uncertain principle, which says that this constant delta uncertainty in position and momentum is a constant, right? So if you want to detect anything like very small, its position is very small or size is very small, you need very high energy, high momentum. So that's why you need accelerator methods. But now if you look at this scale, like if you go from electron size to quark size to compare with atom or molecules, you see that there is a huge, like you will gain of the order of 10 to the 8 or 10 to the 9 size order, right? Now if you adopt follow this, so that means if you want to probe the similar kind of physics using atoms or molecules, you don't need that much energy. That's why Amar was talking about EV or that kind of order. That like if you want to measure something, so then if you can like perform this kind of experiments on atoms or molecules, you can do actually in the laboratory using this kind of facilities. It's called tabletop facilities. Okay. So now let us see that what kind of how we can infer those kind of physics. Now, if you consider atoms, we have electrons and nucleus. So generally, we consider electromagnetic interactions due to the exchange of photons. But generally, we neglect there is like it will like there could be also another like particle that is coming from the standard model of particle physics that is known as Z0 boson, and that can also exchange between electron and a nucleus. But if you allow that, then it will give us weak interaction. Generally, we neglect that because in the the effect of this particle in the energy spectra is so small that you cannot observe or the precision at which you are looking at, that is not interesting. Okay, so that's why we neglect that effect. But if you include that, so then there will be like some kind of parity violating effects in the atomic systems. But the question is, like, if you have this kind of weak interactions between electrons and nucleus, then the coupling coefficients that you want to describe using the standard model of particle physics are given here. So this is the coupling coefficient values predicted by standard model between like electron and up quark and down quark and so on. And this value is known as Weinberg angle. So if you substitute these values, so it is of the order of these values. Now for a given atomic systems, okay, so there is a quantity we define is called nuclear weak charge, like electric charge. This is a fundamental quantity for atomic systems that is known as nuclear weak charge, and that is given for different, like for particular atomic systems. Using these coefficients, we can express using this kind of expressions. So this is the expression for a cesium atom. So similarly, you can express like this for any other atoms also. Now the thing is, if you can extract this value QW, there is the principle. I'll tell you how it is done later. But now, if you want to extract this value using atomic studies or molecular studies, that will be model independent quantity. Now that quantity you compare with the standard model value that is predicted, and if you see some deviation, if they agree, that means you can say that standard model is okay. If you see some deviation, that means from that deviation, you can find out some signature about the existence of physics beyond the standard model of particle physics. And then that deviation can be expressed as a mass of some like extra Z boson. That means you can think of that there are some extra Z, another kind of Z boson exists, and that is contributing to this quantity, or some kind of radiative corrections, or even these days there are also discussion that there is interactions between electron and nucleus by exchange of something called heavy photon, or that is also known as a dark photon. Okay, so those kind of particles also one can predict. So these proposals are coming from particle physics models, but that we can predict by studying these kind of quantities. Okay, how we can actually do that? So this parity non-conservation amplitudes between 6s and 7s transition in cesium has been measured very precisely by this Weinman group. Okay, he's a Nobel laureate. And there are two different kind of amplitudes. One is like parity, like nucleus spin independent and nucleus spin dependent, depending on the like how you are doing the measurements. And then there is a quantity here is known as vector polarizability. So that this quantity can be expressed as in the form of this. And here this is a measured quantity that one can measure from the experiment, from the light shift experiments. But theoretically, we can calculate this quantity. This is known as E1 amplitude due to the presence of nucleus spin independent kind of parity valuing interactions. And then this quantity also nuclear like this vector polarizable quantity. So let us say if the measurement is within like 0.5% accuracy, where is the case in cesium, and then we can perform the calculation. Okay, here this quantity 0.5% of calculations, and this also can be either calculated or you can extract from the experiment like within 0.5% accuracy. Then by combining these three quantities, we can extract the value of QW. So now you compare this QW value with the standard model value, and if you see some difference, that will help you to interpret the BSM physics. And this is another kind of phenomena, like as we mentioned that today we see more matter than antimatter, and that is coming from the cosmology, this signature. So now the kind of like this, like if you want to explain this physics, why we see more matter than antimatter, it's because of some kind of CP evaluating effects. It's called semi-leptonic kind of CP evaluation that causes this kind of thing. That's a prediction. Now, if you want to prove that, so there is no direct evidence to that, but there is another indirect way for proving that. So if you can measure the like size of electron or quark, okay. So if you do not take into account this semi-leptonic CP evaluating interactions, the size of electron or proton, quark will be different than if you assume such kind of interactions. So now if you take a standard model of particle physics, the size of electron can be estimated using like considering these kind of interactions, and that comes at the higher order of perturbation level. But if you take supersymmetric model, something like that, this will come this kind of CP evaluating effects, or the size of electron can be enhanced due to this kind of effects. And if you can measure that and find out the exact value for the size of electron, from there also we will try to prove that such kind of like CP evaluations exist or not. That is predicted by SUSI model, and then ultimately using that kind of physics we will be able to understand this matter antimatter asymmetry. So this there are several experiments are performed on this electric dipole moment of atom. So let us say if electrons or quarks, they have like CP evaluating effects, that means their sizes are enhanced because of the CP evaluating effects. That will also, you'll see those effects in the atomic systems or molecular system in the enhanced form because of the internal electric field effects. So because of that, so people try to measure these effects in atoms. But if you like in molecules, even they are much bigger. That's why there are many experiments are going on in molecules, which actually Amar did not emphasize. He's actually performing the experiment on thorium oxide molecule. So these are atoms, and these atoms, if you combine with atomic calculations, from there we can find out the size of neutron, okay, and like dipole moment of neutron, dipole moment of proton, or even up quark, down quark, and so on. Okay, and as you see here, like we're combining the external result, result from the mercury, which is more like accurate compared to other like atomic systems. So using like combining with our calculations, so these are the values we have got. And now if you compare with the standard model of particle physics, you see there are like almost 10 orders difference or 5-6 orders difference. That shows that there is some indication that like some kind of BSM physics we are able to prove by doing this kind of studies using atomic and molecular physics. Okay, so there are also other like fascinating things people are trying to do, study using atomic systems. There is another way of like proving this local Lorentz symmetry violation in the atomic system. So this experiment was conducted in US. So what they had done is they had considered this calcium ion, then they had tried to measure the like interference between this the electron which is was in the ground state, that is the mj equal to half state, to in the d5 half state with the mj value equal to plus or minus 5 half. And by doing that, so they had detected some kind of this kind of experiment they had performed, and they had seen the change in the energy levels because of this kind of measurements. And so from there they had seen that there is a slightly signature of variation of this local Lorentz symmetry violation. So local Lorentz symmetry violation means indirectly also it is like violating Einstein's equivalence principle. Okay. So now if you want to study this kind of physics, so one has to consider this kind of interaction Hamiltonian, where you have these coefficients. So these are the operators which describes the Lorentz violating interactions, and these are the corresponding coefficients. So by calculating the matrix elements of these operators, we can actually predict these values and then compare with the general theory of relativity values. Okay, so that is how we can also predict this Lorentz symmetry violating interaction coefficients using atomic systems. So this topic has been already discussed here by Professor Ridley. So now what is this atomic clock, how it works? So to explain to you that, now let us try to understand the properties of wave. So these are the typical properties of wave. So where using these properties, now if you want to see define the time propagated by some wave, so we can say that the number of oscillation time times the period of the wave, if you can find out, then you can say that for how long the wave has been propagated, that is the time. Now from this definition, now if I want to define this unit of time, that is 1 second, then I can find out if I can find out the duration for oscillation, how much time it has taken. So that will give me 1 second, and that is just equal to 1 by frequency, right? Because they are conjugate to each other. Now in the atomic systems, atomic system, when I say it could be atoms, ions, or molecules. So the energy levels are fixed, and we can reproduce them anywhere we like. Okay, so that means if we can measure the transition frequencies, this between the atomic energy levels, those transition frequencies can be used to define this second. That is the basic principle of using atoms for defining as clocks. And what are the basic requirements for that? The long lag time, it was already discussed. That means narrow line width, and these transitions or the states associated with the transitions should be least affected by the external forces like electric field, magnetic fields, and so on. So now based on that, so we can divide the electronic levels of atomic systems as electronic levels, which could be in the optical region. So then we can have optical clocks. If we can consider fine structure splitting and the transitions among them, that could be in the either optical or terahertz range. Then we can have either optical clocks or terahertz clocks. So here one can consider this highly charged ions, and or the transitions between high profile levels. Okay, so that is basically will give us microwave kind of clocks. Now, if you look at the periodic table, we have so many elements, and here actually in principle almost all the elements can be used as atomic clocks, but some of them will be used in the neutral form, some of them will be used in the ionized like single ionized form, double ionized form, or multiple ionized form. So then you can have several atomic clocks, and importance of having several atomic clocks were discussed already yesterday and day before yesterday. So now thing is, now if you want to find out which candidates or which transitions are important for making atomic clocks or suitable for making atomic clocks, you cannot perform experiments everywhere. Okay, that is not feasible. So that is where the role of theoretical study comes. Then we can find out the transitions by finding out that by calculating various properties that which candidates or atoms or ions are they can be considered for atomic clocks. Then we can also help them, if they have somebody set up some atomic clock experiments, it was discussed strontium, yttrium ion, and mercury, and so on. Then we can also estimate this black body radiation shifts, because if they want to estimate systematic effects, they have to perform separate experiment for that, and that was also highlighted for cesium atom, right? So instead of that, let us say we have potential many methods, and we can estimate this behavior shift very precisely. Then instead of spending time or efforts for conducting another experiment, so you can take the values from the theory. And also if you want to estimate Stark shifts or predicting even magic wavelengths and so on, or effects of magnetic fields, they are the roles of atomic theory will play. Okay. So now if you have high precision atomic clocks, where you can use them, like we can use them for navigation, geomapping, that is well known fact. We can also use them predicting eruption of volcano, or estimate, we can predict also when there could be earthquake. So those kind of things we can predict, and also we can use them for studying some kind of fundamental physics, like verifying the variation of fundamental constants like alpha fine structure constants, or mass of electron, mass of protons, and so on. And we can also detect the existence of dark matter using such kind of atomic clock, if you can have in the our laboratory. Okay, now this here it comes, it's a little I think people will start getting scared by looking at this kind of expressions, but I'll make it very simple. But if you don't understand, you can ask me questions. See now how we estimate this kind of systematic effects theoretically. Okay, so now when you apply laser, okay, to the atomic systems or molecular systems, so the interaction of Hamiltonian you can express in this kind of form. Okay, that I think many of you must be familiar, even you are experimentalist. So then due to this kind of interaction of Hamiltonian, so if you want to see the perturbation in the energy levels, so then the first order effect will be 0, because this will give you, because this is order under parity. So you will start getting the contributions from the perturbations from the second order effects onwards. Okay, so that can be expressed in terms of polarizability, that is given here. And in other words, we can also express that as a expectation value of some kind of effective Hamiltonian. That expression is given here, the effective Hamiltonian. So this polarizability basically we express divided into 3 components. One is scalar component, then vector component, and then the tensor component. So what we do is we can calculate these components like scalar, vector, and tensor components separately using this kind of formulas, provided you can calculate these matrix elements and energies very accurately using the many-body theory, if you have appropriate many-body theory. So then once you have these polarizabilities, and since experimentalists, they know how much electric field they are applying, using that they can estimate the energy shifts, which is second order Stark shift. Okay, that is where we can actually help. And since these are like heavy systems, the atomic clocks are performed in the heavy atomic systems, so these wave functions are actually Slater determinants. So that is where the complication lies. Okay. Okay. So that was like for atomic states. Now even there was like a discussion about the Stark shift in the cesium atom. So in the cesium atom, the if you consider in the ground state 6s, so the atomic clock transition is between hyperfine level f equal to 3, f4. So this is the transition people consider, and this is a hyperfine level. So what I was talking about in the previous slide, that was using the atomic states. Now if you want to calculate the wave functions of hyperfine levels, this is little complicated, because this will have wave functions from the JMJ like atomic levels, and with a direct product with the nuclear wave functions. So we cannot deal with the nuclear wave functions, because that will be very complicated to handle. So what we basically do, so we write this as something like, so this we consider a 0th order wave function. Then this one, so this one we write as a first order correction due to the hyperfine interaction. So then you can have some kind of like JIMI states, intermediate states, then JIMI with hyperfine interaction, then JMJ divided by the energy denominator. So what we are doing, so these hyperfine levels has atomic energy level, atomic contributions, then you will have first order corrections due to the hyperfine interaction. Okay, so when you are trying to find out the Stark shift differential polarizability between these two states, so these contributions from the atomic part will cancel out, because they are coming from the same 6s level, but you will have contributions from this this first order perturbed wave functions due to the hyperfine interactions. So that if you want to calculate the polarizability contributions due to this part. So that is what we call is a hyperfine induced polarizability. And the expression for that expression, state is little complicated. It's little messy, which deals with this is hyperfine interaction Hamiltonian, and these are the electric dipole operators, and so on. So it will have three different contributions. Okay, we call it a normal, center, and something like that, top, central, and normal contributions. Then you have to calculate this kind of quantities. Then if you can provide them, then they can estimate the Stark shift and as well as BBR shifts. Okay. So this is the expression for BBR shift. Now, if you want to estimate BBR shift, so this is the like electromagnetic interaction field that you have to consider in the relativistic theory. And if you do the multiple expansion, so and try to find out the energy shift due to this expression, so one can express using this kind of like expression, which will have a temperature dependent. Okay, and this is called the polarizability. So depending on the kind of operators, like if it is dipole operator, then you will have like U1 BBR shifts. If it is M1 operator, then it will be magnetic dipole polarizability, and the contribution due to magnetic dipole polarizability. And if it's an E2 operator, you will have electric quadrupole contributions and so on. You can also go on adding higher order contributions, but typically we go up to only quadrupole polarizability expression. Okay, so now using this kind of expression, so if you have the appropriate many-body theory, you can estimate this kind of polarizabilities, and using those polarizabilities, experimentalists can estimate the systematic effects. It's not only for atomic clocks, for any high precision experiments. So these theories are actually valid. Okay, now similarly, if when you apply electric field, so there will be also gradient of electric field associated with the field laser. So that when it interacts with the electric quadrupole moment of the states, so that will give us electric quadrupole shift in the system. And if it's a hyperfine level, the expressions will be like something like that in the up to the first order perturbation. And if it so that can be also related with the atomic quadrupole moment, and using this you can evaluate this quadrupole moment of any atomic systems using these expressions, and the corresponding operator is given here. And then using this expression, you can estimate this quadrupole moment of hyperfine levels, and from there you can find out the quadrupole shift for any hyperfine level states. Okay, so these are the this is where we can the theoretician actually comes they play the roles to help the experimentalist. And the other kind of systematic effects is quadratic Zeeman shift, because generally the first order Zeeman shift, the linear Zeeman shifts cancel out by selecting m equal to 0 levels. So then the leading order the Zeeman shift comes from the quadratic part, and that can be estimated using this interaction Hamiltonian. But this part comes from the due to the hyperfine interactions, magnetic dipole hyperfine interactions, and this is due to the electron angular momentum interacting with the applied magnetic field, and this is coming due to the electron spin interacting with the applied magnetic field. If you can estimate this, so this value one can estimate using this kind of expressions, nuclear gyromagnetic constant for electron GJ factor. So one can use this kind of expressions because these are bound electrons. So you have to use the this kind of expressions to estimate GJ factors, and this hyperfine structure constants also can be estimated using this kind of expressions. And once you know these values, then they can estimate the Zeeman shifts. Okay, so that is how you can estimate the effect due to the magnetic fields. And what else can be done using these atomic clocks? So this when you consider as I told you, this in the atomic clocks, people consider hyperfine levels or fine structure levels or electron levels and so on. So if you consider hyperfine levels, these energy levels are functions of gyromagnetic constants as well as this alpha fine structure constant. So if you are trying to measure the ratio of two clock frequencies, okay, so if you believe that alpha or these quantities vary over time, then you can use and these are sensitivity coefficient due to the alpha. Okay, so then from these measurements, and so this has to be calculated using theory, and if you combine that, then from there you can predict whether alpha varies over time or not. You carry out them this frequency ratio measurements over the period of time, then by combining those experimental data with these calculations, one can actually prove the variation of fine structure constants. And if you use optical transitions, one has to use this kind of expressions. And if you combine this either like a hyperfine with optical, so then one has to use this kind of expressions. And once you find out the variation of alpha, there is a signature of that, and that can be related with the variation of mass of that quark, okay, here, and or electron, or there are some fundamental quantities called QCD parameters and so on. So they can be also proved using this kind of studies. So that means we need both theory as well as experiment. So without only with the experiments, you cannot prove this kind of things. Okay. Now this is the most little some people get they feel it's complicated, but I'll try my best to make it very put it in a very simpler way. That how why this called many-body theory and why the many-body theories are complicated for atomic systems. Now let us understand that point. So as you know that so this is in the textbook, you will find out that when you try to solve the wave functions of hydrogen atom, so the Hamiltonian is given here, so that kinetic energy term and nuclear potential, and in the relativistic form you have the corresponding Hamiltonian here, and you know that the wave functions for this Hamiltonian we can solve exactly using the analytical approach. And here the outcome of that is we can have analytical solutions, and all the states are described by using quantum numbers like principal quantum numbers, angular quantum numbers, parity, and so on. And they are pure symmetric because the potential is spherical symmetric here. Okay, but when we are going for these multi-electron systems, heavy electron systems, heavy atomic systems, then we have one additional term, that is the interaction term between the electrons and electrons, Coulomb interactions or Bright interactions, so on. And then I'll show you why this term makes our life difficult. In the relativistic form, so this will be the form, but again let me tell you that these are actually approximated Hamiltonian. But in the even this is also approximated, but if you try to include the finite size of the nucleus or finite mass of the nucleus, then the actual Hamiltonian of the atomic systems will be written like this, where this will be the kinetic energy of the nucleus, and then this nuclear potential also will be a function of nuclear charge radius. That means that will also depend on the size of the nucleus, and so on. Okay, so that means if you use this Hamiltonian instead of these Hamiltonians, what it means is, and you try to calculate the wave energies of different isotopes, you will see different change in the energy levels. There will be a slight change in the energy values from one isotope to another isotope, and that is known as isotope shifts. And how we arrive from this Hamiltonian, so this is by changing the coordinate system, by using this relative coordinate system. And then this Hamiltonian can be expressed as into several parts, like nuclear contribution, which we can neglect because we try to measure the energies with respect to nuclear contributions, so that generally we don't take into account that. But then we have this the Hamiltonian I showed you in the previous slide. Then there will be corrections due to the finite size of the nucleus to the kinetic energy term is known as mass shift, and then due to the size of the nucleus, volume effect, that is known as field shift. And this expression for mass shift is given here. This is basically another kind of two-body interactions. It is the interactions due to momentum with momentum between the electrons. But when you make I equal to J, that is known as normal mass shift. And when I not equal to J, this is called as specific mass shift. That is further divided because this becomes one body term. This remains as two body term. And this is the field shift contribution, the interaction Hamiltonian. Now, if you want to estimate the correction over this Hamiltonian that we are calculating generally, that then we have to use this interaction Hamiltonian and treat them up to first order or second order perturbation up to the precision that we are interested. Then try to find out how much energy changes from one isotope to another isotope. And this can be done using this kind of approach. And for that, for convenience, we use some constants called normal mass shift constants, specific mass shift constants, and so on. And this field shift is expressed, it becomes a function of this square of RMS radius of the nucleus. Okay. Now there is something called King's plot. Now if you have two transitions in two different isotopes, and then you plot their ratios, okay, then you will end with one kind of equations like that. And if you can measure this, like isotope shifts, in two different, transitions in two different isotopes, and then from there you can extract actually these values, the massive constants, field shift constants, and so on. Okay, and if you have, like you have calculated, some of these constants, and combining with that, we can actually extract the value of nuclear charge radius. Because if you want to directly calculate nuclear charge radius of different, nucleus, it's very complicated, because nuclear theories are very, like, not even that is very complicated to solve, calculating nuclear wave functions. But this is the indirect way of extracting the nuclear charge radius. Okay, but there is another concept to that also. That is why I just wanted to introduce this, this part. Like people also believe that there is one new kind of vector boson that can exchange between electron and nucleus. And if that happens, then that will, like when you try to measure the isotope shifts, okay, then these contributions, these new interactions also will contribute there. And if such contributions are there, then there will be, like, if you try to plot this equation, you will see a slightly deviation than from the straight line. Okay, and from that deviation, one tried to find out whether such kind of particle exists or not in the nature. Okay, so this is a new concept, and for last 3-4 years, you'll find many papers in Nature, or even many PRL papers and so on. So at least since you people are from AMOPH, atomic and molecular physics background, at least you should be aware of this. Okay, now let me come to the other, like this one, how we try to estimate the systematic effects that I try to highlight it. Like now let us say when you apply external electric field, what happens that if external electric field is like very strong, then we cannot use the perturbation theory. Okay, but if it's very weak, so then what we can do is we can make use of the wave functions that we have already calculated using the atomic Hamiltonian by expressing the total the modified wave function as the unperturbed wave functions due to the atomic Hamiltonian, and the small correction due to the electric field, and then these corrections will come from the states having different L compared to the original state, and because with the opposite odd parity or other parity states, and that is why the here the exact state will not, it will be admixture of different kind of parities. So that's why if you have strong electric field, then you cannot treat parity as a good quantum number. Okay, and solve, so then the solution will become very complicated. That will be challenging. Only for electric field we can make this kind of assumptions, and that means we can solve only the wave functions of this atomic Hamiltonian, then try to use this kind of approximations and try to estimate the change in the energy levels. And similarly, if you have magnetic field, then the total angular momentum is not a good quantum number. That also you have to relax. Otherwise, if it's a weak magnetic field, again you have to treat in the similar way. Okay. So as I told you, so when we consider this kind of Hamiltonian, so the challenging part is this one. That makes our life difficult, because what happened is, now when you consider this Hamiltonian, it's not acting on psi. So this psi is actually, it's a Slater determinant of single particle orbitals. You can call psi 1 electron 1 with R1, psi 1, R2, and so on. Okay. So now if you expand, because this also there is a sum over I, that means all the electrons here, and there is sum over Ij. So if you expand here, so you will get expression something like H, that is one body operator, the kinetic energy term and nuclear energy term, psi I. Then you will have small psi I, that is the single particle orbital wave functions, and plus you will have 1/2 Ij. Then psi j, okay, yeah, psi. Actually, you cannot. There is one step I'm actually, because of the lack of time, I'm leaving that. So this is the Coulomb interactions term, psi j, then psi I minus, you will have corresponding exchange term here, is equal to sum over I epsilon I phi, psi I. Okay, so if I remove sum over I, so then this is the equation you are trying to solve. But earlier when we are trying to solve for the wave functions for a hydrogen atom, we did not have these terms. But now when we are trying to solve the wave functions for these individual electrons, so then it depends on the wave function of other electrons. So that's why it's not possible to solve this equation, and that makes our life complicated. So how to handle with this? That instead of using the actual Hamiltonian is this term, Coulomb interaction term, so we'll replace that by one kind of effective Hamiltonian or effective potential that will be a form of one body operator, and that we call mean field potential. Okay, effective one body potential. And if you replace that, that means this has to be constructed out of these interactions, so that most of the interactions are included here. Then the rest, what you are neglecting, that means this is two-body interactions, denoted by this notation. So this part has to be very small. Okay, so then we can neglect this part and consider only this Hamiltonian, only considering this like one body part up to this, and this effective like a potential here, mean field potential. Then we can easily solve wave functions for this Hamiltonian, because the entire like operator will be just sum over Fi and Hi. So this H naught or HMF will be just Fi, just Fi one body operator. So it will be like a hydrogen atom problem solution. So it will become easier for us to solve. So that is the approach we are adopting. So now how to get this mean field wave function? So once you have this, so then you will have the solutions like that. So it will become a simple equation like a hydrogen atom solution. Okay. Now here, how we solve this kind of equation using a variational principle. Okay. So that means the actual wave function, this I mentioned here. So that is like expressed as a like known wave function, or is a mean field wave function with a slight deviation from here, for which we can't solve the like these wave functions exactly. And if you can minimize this arbitrary quantity here alpha, then we'll try to approach like this solution, guess solution will be very close to the actual solution. Okay, so using this kind of a trick, and by minimizing this equation energy with respect to this alpha, we can find out this kind of equation is called Hartree-Fock equation, and that gives us the like mean field solution, and that solution will be very close to the exact psi. Okay, provided only for the energy part. Okay, I'm only talking about the energy part, but this may not be true for any other properties. Okay, so once you have that, so that means like let us say, so that wave function, that is again, it's not for like for some qualitative analysis, that calculation is okay, mean field calculation. But if you want to have high precision calculations, then the quantity you had neglected here, this is called residual interactions, we have to also include contributions from those interactions. Okay, so how to do that? So the way we are doing is, so that exact wave function psi naught we wanted to determine, that is divided into two parts. Like the part for which we got the solution using the mean field approach, and then the rest, that like from the entire Hilbert space, what we could not like we neglected, that we call orthogonal space. So this is known as model space, and this is known as orthogonal space. And then if we can get the solutions from this part, that P plus Q would give us the entire solution. Okay, so how that is done? So by actually what we know from this mean field solution is only phi naught. We don't have any information about Q, but we can define one wave operator, okay, which can which when acts on this phi naught can generate this this Q space. Okay, so it's known as wave operator. So once we like, that means this like omega should include P as well as Q. Okay, so that's why this omega will also have one plus something that will generate contributions from this that's why this Q is written 1 minus P, and then you will have the entire solution. So now when we use different kind of many-body methods, when you say perturbation theory, okay, or if you have heard about configuration interaction method, or somebody was talking about couple cluster theory and so on, depends on how you define omega. That is all about the many-body theory. So the idea is how you define omega and how much it is able to capture contributions from Q. That's all about the many-body theory. Okay, so there is a way of defining whether the kind of many-body theory you are using is actually very accurate one or not. So to define that, we have some kind of a behavior. That means if you develop a many-body theory, if it satisfies size consistency or extensivity property, then you say that this kind of many-body theories are accepted. What it means that means you have a system like having n number of particles. What you do is virtually you divide into two parts, n by 2, n by 2. Then you calculate using the same theory, calculate the energies of two subspace. Then you just prove that whether your total energy that you calculated for the entire system is satisfying this kind of properties or not, or the wave functions. If they are not satisfying, that means we will not accept those kind of many-body theories. Otherwise, we'll say that these are valid many-body methods. Okay. So now when you apply perturbation theory, okay, let us say we have the mean field wave functions. How I am doing with the time? You have still time, 45 minutes, right? So see now let us say I have the total Hamiltonian. So this is my mean field wave function. Okay. So this is the residual interaction. Now I can treat these residual interactions perturbatively using perturbation theory. So then the total wave functions I can write down as the mean field wave function. Then the first order corrections, second order corrections, and so on. Similarly, the energies can be written like that. Now, if you have two, one is this is internal actually perturbation. This is not the actual perturbation. This is coming from the construction of your many-body theory or the way you try to solve the problem. But there is if you want to include the contributions from external field, due to whether it's electric field or magnetic field or due to the parity non-conservation effect or magnetic field and so on, then there will be another interactions you have to also add into the your Hamiltonian. So then this becomes more complicated. Then your perturbation theory will look like this. Okay, so it will look very complicated to handle that, but this is how you have to handle. But then there are also different ways to solve the wave functions in the perturbation theory. One approach is called Brillouin-Wigner perturbation theory, where the expressions will contain the exact energy of the system. Okay, but this theory is the advantage of this theory is it will converge very fast. Like when you calculate first order to second order, third order, so then the up to third order you will get almost all the results. But the problem is it has size consistency issues. But then this is the most popular method in the perturbation theory. It is known as Rayleigh-Schrodinger equation, where this it doesn't include the total energy, but it includes the calculated energy at each order. Okay, but this one will take time. That means you have to go beyond 6th or 7th order to get the conversion in the calculation. But at least you will not have this kind of issues here. But this is more challenging. That's why to get the wave functions accurately using this kind of perturbation theory is not possible. So we have to look for something called all order perturbative method. So what we are doing in that approach is, so that means the total wave function we are writing as a linear combination of 0th order wave function, then all possible kind of single excitations with respect to this. That means the number of orbitals you have, you allow electrons from each orbital to excite as many as virtual orbitals and so on. So it will give you one electron at a time excitations. So that will give you the single excitations, then double excitations and so on. If you have n number of electrons, you will have n tuple excitations, and the total wave function can be expressed like this. So this will be exact form, but going in this form, if you want to go beyond double excitation, triple excitation, because it's not only one double excitation, all possible double excitations. So the at the for example for cesium atom, so the number of double excitations you can anticipate up to 8 or 9 or something like that. So that many number of double excitations it will generate. But if you talk about triple excitations, unless you have big supercomputers, it is very difficult to handle that. Okay, so that's why you have to truncate this series at some point. But if you once you truncate this series, then it gives you size consistency problem. So then we cannot use this kind of methods for high precision calculations for the heavy systems. Okay, but alternatively we use some method called coupled cluster theory. What it does, it has the same principle, but then the waveform, the wave operator is expressed in terms of exponential form, and it has operators ti, ii, and so on. which means this is all possible single excitation, double excitation, so on. This operator will take care of all kind of excitations, but it is in the exponential form. Now what happens if you truncate the series, let us say up to doubles or something like that, because it is in the exponential form, and when you expand, you will have t square, ti square, t2 square, t3 square, and their cross products ti, t3 like that. So they will also capture contributions from triple excitation, quadruple excitations, and so on. So that is how it compensates that size constraints issue and gives you more accurate result. So these are all order perturbability methods, because there you don't have any these coefficients include all order, like residual interactions up to infinite order, the way it is solved. Okay, so this is the advantage. So that is how you are using coupled-cluster theory. And then to understand the level of excitations and deal with that, so as a theoretician we use diagrammatic techniques so that we understand what is single excitation, double excitations, and which effects play more important roles, and so on. Then when you want to calculate energies, and this is the expression. Now if you follow that using coupled-cluster theory, it becomes a non-terminating series, because you see it's exponential to the t dagger and so on. There is no end to that. But we play trick, so we rewrite this expression in such a way that we will get only finite term. But to arrive at this point, so one has to impose this condition, and this condition, by imposing this condition, we get the wave function, the amplitude of these t operators. And once you get from this condition, if you get the t amplitudes and then substitute, then you can use this expression to get the energies, and then you can easily handle that. Okay, so this is the trick we use. But thing is, that was because this you can use because this you get this expression because of this condition for the energies, but the same condition you cannot apply for calculating property of any other operators. So the expression remains to be like non-terminating, and it's a real challenge. So you have to, so that if you use this kind of expression, it doesn't satisfy this something called Hellman-Feynman theorem, which is another fundamental quantity. So we have to get rid of that. So then how we can do that? So there is also something called finite field theory. So in the Hamiltonian, you can include like interaction Hamiltonian by putting some arbitrary parameters, and then calculate the wave function or like energies with h naught first, then using this total Hamiltonian. Okay, then if you choose lambda is very small, okay, then the calculated energy you can express like that. The faster energy correction will actually be, it will correspond to the expectation value of that operator. But the problem is, while doing that, see, you are neglecting the third order, second order and third order contributions like that. So it's always will not give you actually correct result, because this will be that will be numerical instability there. But many people like in molecular people, like those people who are doing molecular calculations, and they calculate polarizabilities using this kind of approach. But this is not actually advisable, because this may not, sometimes it will give you wrong result. It has a lot of issues. I don't want to discuss those things in detail. But here we have proposed another method. So what we can do is, the Hamiltonian again can be expressed the way we had expressed in the finite field approach, but the wave function we can again express as a zeroth order wave function and first order correction. But if you can solve this equation, this is the first order perturbed equation, then you can get the first order perturbed energy. Okay, and this first order perturbed energy is nothing but, like as I told you here, is nothing but the expectation value of the operator. Okay, but then you will get in the coupled cluster framework, you will get some expressions like that, and that is possible to solve. And like if you want to calculate the expectation value of specific mass shift operator, which is another two-body operator, then this kind of expressions are more suitable. But again, it is only for expectation value. But if you want to calculate transition matrix elements, the theory is more complicated. I am not getting into that. Okay, now when we have such methods, that means we want to solve this kind of wave functions. And as I told you that these wave functions we basically write as a linear combination of mean field wave functions. Then along with that, the excited states with respect to the mean field wave functions. And diagrammatically, pictorially, you can see that. And so the number of excitations, if you see up to singles or doubles, I'm not going to up to even triple or quadruple excitations. Even it comes like for lithium atom is of the order of 10⁵, for rubidium like that. Okay, Now, if you want to solve the ground state of this systems, this is a typical number. You can even actually, depending on the basis size and so on, this number can be, even it can be more. And then this is the equation one has to solve for ground state. And when I'm writing A, so this is the dimension of this matrix. A itself is a function of X. So this is the wave function that we are trying to solve. And that itself is a nonlinear form. I have written in a very simple form just for explaining to people. So it satisfies Ax plus B equal to 0. But for excited states, one has to solve Ax equal to Ex. That means X equal to lambda X. And where you have to diagonalize this matrix. It's a n by n matrix. Now you have to diagonalize a matrix with n by 1, then you can understand the kind of complication you have. So direct diagonalization is not possible. So there are special tricks we use. And again, as I told you, this A is a function of X itself. That is a nonlinear, like A will be A plus Ax plus X square and so on. Okay, so it's a nonlinear form. So because of that, we use this kind of systems. Though we don't have tabletop experiments, but this for us this is our instrument. Okay, without that we cannot solve any of these equations. And here I would like to just give you some sample example that what kind of properties we are solving. Like for example, in 2019 we had proposed several ions, highly charged ions for clocks, and all these quantities we had calculated. They were not existing in the literature. Line width, quality factors, everything, whatever you see, polarizabilities and so on. And using that, we had estimated different kind of systematic effects. And it happened that last year, this one of them was actually realized in Germany in his group. So the first highly charged clock. Okay. So I was actually reviewer of one of the reviewers of this paper, and it is published in Nature now. This year also, we have proposed that in ytterbium traditionally only one transition is being considered for atomic clock, ground state 2 3p0. That also he mentioned about in strontium. But we have predicted that there are two more transitions in ytterbium. It can be also used as atomic clock transitions. And if you have that, because you have three transitions in ytterbium in the same atom, which can be used for atomic clocks. So then the systematic effects will be almost similar. So what you do is you measure the three clock frequencies and their clock frequency ratios. And if they can measure that for some time, 2-3 years or something like that, from there we can try to get some information about the variation of fine structure constant. That is the idea. So this was, we tried to get published in PRL, but we were unsuccessful. And this is a paper where what we have done is by combining that new method I showed you. Using that method, we had calculated isotope shift constants, and then the measurements. This is in potassium, isotopes, and then the measurements were carried out at CERN, okay, isolated facility. And by combining this isotope shift measurements with our calculations, the nuclear charge radius were radio of different nuclei were discovered. And then we found that at around n equal to 32, neutron number 32, it showed some kind of magic behavior. Like for nuclear physics people, it's more it's interesting. And then here, by studying parity evaluating interactions in the cesium atom, we found out the some limit to the mass of extra dark boson or extra boson. So there's some limit we had put. And here also studying the electric dipole moment of mercury atom, we had found out the it's called chromoidium of quarks. So they are limit to their values are put. Okay, so these are the kind of studies, high precision studies we can do. We can also estimate a lot of systematic effects. And I have also not discussed many other things. Like anybody is doing any spectroscopy measurements, and theoretically we can help that way. Okay, but there are these methods. I put it in a very simple way, but the methods are a little complicated. But once you start working on that, things will become simpler. It's in any field it is true. Okay, so this if there are any questions or something like that, I'll be happy to answer. There is. Yeah.
When we are finding that isotope shift, so how will you determine that, like, which type of isotope is contributing how much? Like, so it's depending on that their natural abundancy or something else?
No, okay. See, there are two things. So one is, okay, what kind of isotopes are like this one? Okay, let me come to that slide here. See, when you do isotope shift measurements, so measuring isotope shifts for stable isotopes are easier, which you can perform in the laboratory. But basically, you will not find many stable isotopes for any elements except few. Okay, most of them are unstable, so they have to be produced using accelerator methods. So that is why people have to depend on this sun kind of facilities or something. That is number one. Number two is like these isotope shifts, they are transition dependent. Okay, because see what I told you here. So okay, look at this expression, the normal mass shift or these quantities. Okay, so pi dot pj means actually if these are like momentum like interactions, right? So if the wave functions like electrons are far away from nucleus, they will behave strongly. But the other one here, the field shift, okay, so that comes from the nucleus. Okay, so if it's like like light systems, okay, so you will not see much field shift effect. So mostly it will depend on the this kind of interactions. Okay, but again, it depends on which transitions you are considering. But in the heavier systems, this one will it will have a large contributions, not dominant. It will have it will have large contributions. That means if you have like your transitions involve S or P have states, then you will get very significant contributions from this effect. Otherwise, like if you are like your states are like D or F states, something like that, then these like like these interactions will dominate. So it depends on the transition, and also depends on the what kind of isotopes you are considering. So there is no such general rule for, here too, because there will be a lot of cancellations also in the, because it's a two-body interactions. It is very difficult to actually guess that how the like interactions will behave and what will be the final outcome, like unlike hyperfine structure constants or something like that, because it's one body operator. You can guess that from cesium like from lithium to sodium, that will be large enhancement or something like that. But here you cannot guess like this. It's not possible.
I was observing that this matrix size, you were saying when you calculate for lithium between 10 raised to 3 to 10 raised to 5. So why is there a spread? Because you know the atom, so for example, the slide before, yeah, or for rubidium 10 raised to 5. So this is up to you, how many, what is the size?
So there is like in principle you will have infinite number.
Yes.
See what happens. Again, this depends on the property also. I'll tell you. See what happens. You have occupied orbitals. Okay. Then we call it's a defined Fermi level. Okay, where you have the like cutoff like occupied orbitals. So then what we call virtual orbitals. They are up to infinity. You will also have continuums, right? But when like in the perturbation theory, what happens is the energy difference between these two will go into the denominator of the perturbation expansion, right? So when you take high lying orbitals, so the energy like difference will be also quite large. So at some point, let us say around 20 or 25, n equal to 20 or 25, something like that, then gradually you see that it is not coming, they are not contributing that much. Okay, so then you decide that okay, you cut over up to 20 or 25 like that. But then there will be like a hyper like fine induced polarizability. I told you there will be some like quantities because it's a third order polarizability. Okay, so this energy like difference will not appear in the denominator. Yeah. So then there you cannot make this kind of interactions. So then you have to keep on adding and verify at the mean field level that whether these orbitals are contributing or not, then these numbers can even become much bigger. So here, since we are making this cutoff, that's why this number.
So the errors what you quote means in the next slide from the theory. So how is that?
Yeah, so that is again state of art. See what sometimes you do, like you make approximations here. You also make approximations in this kind of excitations, level of excitations, right? Yeah, here also you make where you want to truncate, right? So one way is you make some approximations, then try to calculate some properties where the experimental results are available. Then compare. Then you are sure that okay, some kind of like test. But as I told you, like even at a given level of approximations, you may be able to get one property accurately, but it doesn't mean that the other property will also be that much accurate. So first you repeat that. Then another way is like you first calculate up to singles, doubles, triples, then try to include the higher level excitations, see that how important they are. You can't include exactly, but at least you do some kind of analysis, quantitative analysis, then see that if they are important, then you have to include. Otherwise you say that, okay, because they are coming out, but sometimes that can be also wrong. Okay, but there is no other way to, control this. So that is only the way we can handle.
Any other questions?
Yeah, there is no questions about BSM or something like that. But anyway, so I hope that, oh, you have some, okay.
If there were a young physicist that had unlimited money and time, which of your different possibilities would you recommend him or her to start with?
Yeah, so these studies actually are driven by experimentalists. Okay, initially when we started EDM studies, like during my PhD time, so there was no molecular EDM existing at that time. No experiment was existing because people thought that performing this kind of, because you need to perform relativistic calculations for molecules, and that time molecular theories, relativistic molecular codes are not available. So all the experiments were performed on atoms. Okay, but then once people started learning how to perform relativistic calculations for molecules, and also in molecules like this EDM enhancement factors are like 10 to the 5 or 6 times larger than atoms. Now everybody are accepted to that. That is number one. Second thing is, like if you want to perform this PNC kind of studies, so the calculations have to be performed within 0.5% accuracy, and that is not possible to do in like any atomic, like all atomic systems. Only in few atomic systems one can perform that. So that is a limited choice for performing PNC kind of experiments. So that is one. But this isotope shifts is a new phenomena. Now you know that like in Germany, US, many people are now like they are they got into that. In fact, Peter is also into that. So that is something new phenomena. And also there are many other things like dark matter also, like people are trying to probe using atomic clocks and some kind of things. So those things are some exotic properties that people are trying to probe, but I did not discuss those things here. Dark matter, axion, interactions and those kind of things. But at least dark matter and then isotope shifts, they are like recently they are the more like happening subjects.
More provocative question. How many possible interactions do you have?
So these are driven by particle physics person. If they say that this is possible interaction, then what we say that, okay, if that is possible, let us include that in our calculations. And since you can measure very precisely, okay, you have only the data, right? Either in terms of frequency or energy level or something like that. Then we'll do the corresponding calculations and see that whether from that combination we get any some deviation or something like that. That is signature. Otherwise, one can think arbitrarily anything, right? So that is driven by the when there is a motivation, and this isotope shifts. That idea was existing 4 or 5 years ago. But when people started seeing some deviation in the Kling's plot, then only it picked up. People started getting into the field like that. Otherwise, the isotope shift study is quite too old and people have been doing for last 30, 40 years. Nobody bothered about this new interactions thing. But since now the precisions are improved, people are able to perform calculations more accurately. That's why it has become more popular.
Any other questions?
Okay.
Okay, so, well,
So you have some duty. Okay.
I do have.
One
right?
organizer to another organizer.
And we do have a successful completion of
So you
a
need
lecture
my-
from a lecturer and a topic. There is always a handing over of the elephant, as you have seen.
Maybe somebody has to take the photograph. You can take photo.
Okay, but can you take a photo? So for the record.
Okay.